Okay, students, welcome to the second video in subtopic 11.2. I'm going to talk about AC circuits and generators in particular, and how we actually get that electrical power from AC circuits. I'm going to talk about something called the root mean squared quantity, and I'm going to talk about something even cooler than that. It's called diodes and diode bridges and rectification. Okay. The whole purpose of this video is to talk about how electricity is produced for household and industrial use. Okay. Now, AC generators, again, are universally used to produce electricity. All electricity in the entire world that is used, that is almost all of it for household use or whatever else, is created the same way, and that is from a coil rotating in a magnetic field. Okay. All outlets give an alternating current either 110 volts on this planet or 220 or 240 volts. If you live in America, you're going to be dealing with 110 volts. If you live in many other countries, it's going to be 220 or 240. Okay, and remember, the frequency of oscillation depends on how many times that coil is actually rotating per second in that field. Okay, all right. Now, in order to harness the induced current, what an AC circuit does is it uses these little things called slip rings and carbon brushes, because you see, as it turns, in order to create a circuit that itself is not flipping around at 50 to 60 times a second, you need to have a little conducting ring that's connected to a wire. And that little conducting ring, there's a wire connected to the loop that actually brushes up against it and touches it constantly. You can see that obviously friction is a potential problem, but these rings are designed such that there's very low friction between the wire scraping on the inside of it and the actual circular ring itself. Okay. Now, if we want to find average values from those graphs, remember the four graphs we made in the previous video? We talked about the flux against time, the induced EMF, the current, and the power. We saw that they're all sinusoidal, of course. Now, if we wanted to find the average values, how would we do it? Okay. Well, you'll find that for the graphs that are above and below the x-axis, the average values would be 0, right? Which is not very useful. Okay, so clearly the average voltage is not 0, and the average current is not really 0, because we're actually getting something. We're actually observing a current and an induced potential difference. Okay, in the case of power, because the power was always positive, we could say that the average power was 50. We can look at the graph and tell that. But for these other ones, the ones that are truly sinusoidal, positive and negative, it's really not very useful to look at the averages like that. So what we do is we use something called the root mean squared method. It's called RMS. And this gives us some more useful expressions for averages when things are negative. Okay, they can be found for any function, any set of numbers, whatever. And there's a 3-step process to get the RMS value of anything. Number one, you want to square the quantities that you're given. Number two, you take the average of those squares. Number three, you take the square root of those averages. Okay, let me give you an example. This is example 1 in your sample example set. Okay, calculate the RMS value of the following sets of numbers. Okay, this 3-step process might not be that obvious, so let me just walk you through it. Okay, I'm going to square the quantities. I take each one of these values and I square them. 12 squared, 2 squared, negative 10 squared, 6 squared, etc. Okay, all right, and I take the average of all the squares. So I divide by 10. Okay, that gives me 427 divided by 10, which is 42.7. But then I take the square root of that number and I get 6.5. Note, crucially, that this is not the same as if you just tossed out these 3 negative signs and then took the average of all those positive numbers. It is not the same thing. Okay. Now, I'm barely touching the iceberg of kind of the philosophy and the mathematics behind root mean squared. There's a lot more to it than this. You don't need to know the depths of the mathematics of this topic. You just need to be able to recognize RMS values. I'll teach you how to do that, and to be able to, more importantly, use those equations as given to you in your data booklet to analyze AC circuits. Okay. Now, the RMS value of a periodic current is the same as the DC current that delivers the same average power to a resistor as the periodic current. Okay, so what this does is this mathematically approximates the direct current from an AC circuit as if the AC were itself direct current. So in other words, we're not transferring an AC circuit to a DC circuit physically. What we're doing is we're mathematically modeling if it were a direct current circuit so that we can more easily analyze the math and use Ohm's law to solve AC circuits, okay? So we have, to sum up, we have AC, DC, okay? And there's a combination of the two of these, and this is called AC-DC. And if you've never heard of AC-DC, you know, I've got some music and some videos I can show you of this band from Australia called AC/DC. None of whom, to my knowledge, nobody in this band is an electrician or a physicist, but they have a super cool name. Okay, all right. Now let's talk about functions. Okay, so remember what my function for the my current is a function of time. I had I max times the sine omega t. Okay, now let's find the RMS value for I given that function. Okay, so what I'm going to do, number one, I square the quantities. I square the function. This is I max squared times sine squared omega t. Okay, now using a trigonometric identity where sine squared of x equals 1 minus cosine of 2x over 2, okay, I'm going to transform this equation into I max squared times that quantity. Okay, now notice that over one cycle, the cosine of 2 times omega t averages to 0 over one cycle. So that means that I have, in the end, I have I max squared over 2. Okay? All right. Or, in other words, step 1, step 2, step 3. Okay? In other words, and then if I take the square root of both sides, which after all, what I want is I want the RMS function or the RMS value. It's going to be I max over root 2. And in fact, you see this root 2 everywhere. Okay, so you're given the following in the IB data booklet. Here's your VRMS, here's your IRMS. Turns out that the resistance using Ohm's law, remember how I said that by using RMS values you're mathematically transforming an AC to DC. If you want to use Ohm's law and find the resistance, you would divide VRMS over IRMS. And power is the same way. So the maximum power would be I max Vmax, okay? The average would actually be the IRMS times the VRMS, which ends up being 1/2 I naught V naught. Now, one thing I should point out in your data booklet, it's a little bit misleading. That is, this subscript 0 actually refers to max, okay? It is not the value of these functions at 0. It's slightly misleading, okay? Okay. All right. So, when currents in households is given as either 110 or 220 volts, these are really RMS values of AC current, right? Because remember, what comes out of your house sockets is AC current. So it's 110 or 240, 220, okay? So try this example. What would be the RMS current flowing through a 100-watt light bulb connected to a 220-volt AC power supply? Okay, well, P equals IV, okay? So all you do is you solve for I, and the mathematics is very easy. I get 0.45 amps, okay? Example 3, the RMS voltage in the USA is 110. What is the peak voltage of that alternating current? Easy. Just solve for V naught. It's root 2 times the RMS value, okay? And that's 156 volts, all right? Pretty cool. Okay, an electric oven designed to operate at 220 volts has a power rating of 4 kilowatts. What current flows through it when it's switched on? Again, this is a very simple application of what we did with circuits before, but now we're using IRMS values and VRMS values, and I get 18 amps, okay? There we go, okay. All right, this is a better example. Try this one, okay? A coil like the one shown has an area of 5 square centimeters, rotates 50 times a second, in a field of flux density of 50 millitesla. In other words, the strength of the magnetic field is 50 millitesla. The coil has 500 turns, so now N is no longer 1. I want you to solve A through D. Why don't you pause the video and give it a try? Angular velocity, that's easy. Okay, it's 100 pi radians per second, as it was before. We've already done this previously, okay? How about maximum induced EMF? Well, that's going to be what is that going to be? That's going to be NBA times omega, right? Because that's when the sine function is equal to 1. So I got 3.9 volts. The RMS EMF, it's just the maximum EMF divided by root 2. That's 2.8. And of course, it should be less than 3.9. If it's not, something's wrong. Okay. If the speed of rotation is reduced to 25 revolutions per second, what is the new RMS EMF? Okay. Well, and that you could grind through all the numbers again, but notice that this is just 1/2 of what it was, so it's going to be 1/2 of 3.9 is going to be the new EMF, the maximum induced EMF, and then the RMS voltage is going to be that divided by √2, which is 1.38 volts. Okay, I'm going to talk about something, one of the coolest things in all of our study of circuits, and it's called diodes and diode bridges. Okay, remember that an alternating current produces a periodically reversing potential difference and therefore reversing I. Okay, so power delivered through such a circuit will actually flicker, and in this particular case, I'm rotating a magnet and a bunch of coils, which is causing an LED to light up. Okay, turns out that an LED is itself a diode. I'm going to explain what that means in just a minute, but the point right now is that notice that when you turn that magnet, you get a flickering light. Okay. So how do we avoid this? Because like if you're reading or I don't know, doing something else where often you don't want a flickering light, that can be kind of annoying, give you a headache. Okay. So what we do is we actually are now going to physically convert AC to DC by using what's called the diode bridge. And before we understand what a diode bridge is, we have to understand what a diode is. In a circuit, this is the symbol right here, okay? And this is what a diode looks like. It's any device that allows a current to pass through it in only one direction, okay? Pretty clever. Don't worry about what's happening inside of that diode. Don't worry about the theory or like how it works. We're just going to actually apply it in circuits, okay? Now, you know that current flows only when there's a potential difference. When the potential at one side, call it side A, is greater than the potential at side B, we get a current flowing, okay? And so we get a positive current and then a negative current, positive current, negative current. So what a diode does is it only allows current to pass when it's positive or when the potential difference is one particular direction. The current against time graph will therefore look like this. When it's positive, it will be non-zero. When it's negative, it will actually be 0. So you have basically all these humps here, and then you have 0 current coming out the other end, okay? All right? So the net result is that instead of negative current, there's just simply no current. There's no negative current whatsoever. There's a special term for this in physics, and it's called half-wave rectification. You need to know that term. That's very, very important, okay? The obvious disadvantage to this is that I've lost half my power, right? I had this potential difference, then this current. I've basically shut off half the current, okay? And I still have the problem of flickering power. In fact, it's even worse, right? Because now I have half a period with no power at all, okay? So I still have times when the light is not lit, but that actually lasts longer, which is even more annoying, okay? Now, there is a way to avoid this, and it's called by using a diode bridge. This is what a diode bridge looks like. I'll show you guys some of these in class. It's a very, very clever device, and here's how it works. You set it up in a circuit like this, okay? Let's consider that you have a source of an alternating current. That's what this little symbol here means. And you have a higher electric potential on the left side than you do on the right side. Okay? All right. Now, if we talk about conventional current, we're always going to be talking about conventional current in circuits, okay? Then this current, which I'm calling positive by virtue of it going clockwise, it's going to come through here. When it gets to this junction right here, it's not going to go through D. It's only going to go through A because A, there are two diodes, but the diode in D is backwards, so it's not going to let it go through. Okay? So that current comes through A. Over here, again, it's not going to go through B. It's going to go through the load. And what the load is that's the thing that's connected to whatever device it is that you want to actually harness that power or that energy per unit time from. Okay? Goes through that load, comes back down, and then it's going to exit through C and go back out here, again avoiding B, and it's going to go back to the potential difference source. Okay? There's no current through diodes B and D. Okay, so again, enters through A, through the load, through diode C, and back to the cell. Okay, now In the case that the current is going the opposite direction, I have to warn you, I'm calling this negative current, but that's a little bit misleading because it's still going from positive to negative. It's just that it's alternating, so it's flipped, okay? But I'm calling it, for want of a better term, negative because it's now going counterclockwise instead of clockwise. In this case, the current comes out here, and the same rationale applies, okay? It's not going to go through C, it's going to go through B. Comes through B, it's not going to go through A, it has to go through the load, comes back down through D, and then continues back from where it came from. The important point is that notice that in each case, the current through the load, which again is connected to the device that we want to get that energy or power from, the current is in the same direction. How clever is this, all right? It's really awesome. So the total output to the load is going to look like this, and it's going to be positive the whole time. It's going to be all these humps. Whereas before, in this blue part with half wave rectification, we had no blue wave, okay? Now we have a wave when it's negative, okay? This is called full wave rectification. You need to know the difference between half wave and full wave rectification, okay? Now, does this solve our problem of the flickering? No, it doesn't really, right? It doesn't really, because we still have these little momentary lapses, these momentary times where it goes down to 0, okay? It turns out that the way we get rid of that is to use what's called a capacitor to actually sort of bridge that gap. What a capacitor does, we're going to spend a lot of time talking about a capacitor, is it stores energy and it's able to discharge energy with a certain period or frequency. And if you time it just right, it can actually discharge energy right at these periods of time such that you get a nice smooth graph. It's pretty cool. Incredible that someone invented that. Anyway, we'll figure that out later, okay? You do need to be aware of other ways to draw a diode bridge. If you study these two diagrams here, you'll see that these are effectively the exact same diagram I had before, but now the load or the device is taken out. It's no longer in this box or in between these, but it's the same circuit, right? Okay, right here and right here, the wires are not touching. They're actually going one's above the other one. Okay, all right. Both of these will result in what's called a full wave rectification. And this is kind of nice. Here's the original sinusoidal signal. The top one, half wave rectification. There we are, losing half our power. Full wave, okay, and all these little sort of divots or canyons in between. Okay, we still have flickering, but again, it's going to be minimized by a capacitor. The whole point of this is converting. We have now physically converted AC to DC. There's no polarity reversal. It is now all direct current. So we don't have back and forth. We don't have flickering. We don't have all these things going on where things are positive, negative, and so forth. So it just makes it a lot easier. And now we can then apply Ohm's law to the circuit.